Yeah, I'm fine.
All right, well, welcome back. The next speaker is Carsten Ziegler from Adobe Research Switzerland, and he's going to talk to us about distributed eventing in OSGi. I was reading his bio earlier, and I noticed that he has 25 years of experience in being an open source contributor. That's more than the age of some of the attendees here.
Yes, I'm old. Sorry.
He's a contributor to Apache Sling and Felix. He's also a participant in OSGi Alliance's core platform expert group and enterprise expert group. And he's going to tell us about distributed eventing. I'm interested in this talk because I was telling him earlier that I've implemented distributed eventing 3 times, and it's always different. And the constraints and requirements change the architecture completely. So this proves the ribbon that I picked, which probably you can't read it in the back. It says, been there, done that, but it's always different. If I were to do it 4th time, it'll probably be very different again. So over to you, Carsten.
Thanks, Anish. Yes, welcome to my talk about distributed eventing. Anish already covered all of my details I have on my slide about me, except the email address or the Twitter handle if you want to reach out to me. Okay, so let's get started with distributed eventing. As Anish said as well, a lot of people are doing it, and they're doing it several times in different flavors. And I'm today presenting different approaches related to distributed eventing. I will start with the non-distributed solution in OSGi, the OSGi event admin, and then go into the pretty new RFP 158, which is about distributed eventing. And from there, I will go into some of the use cases that went into this RFP. Because it's an RFP right now, there is not that much to talk about the RFP because it's just gathering use cases and requirements and so on. And so there's no solution or no real proposal right now. And all of the stuff I'm showing here is open source from the Apache Software Foundation. Most of it, or mainly everything, is coming from the Apache Sling project. But I'll start with the OSGi event admin. This is a pretty old specification in OSGi, which simply describes a publish-subscribe model for eventing. So a component can publish an event through the event admin, and interested handlers or listeners are receiving this event, depending on what they are interested in. And such an event is a simple data object which has a topic and a payload. The payload is a key value map of any data related to this event. And the topic is some hierarchical name describing what kind of event this is. For example, in Sling, we are dealing with resources. These are pieces of data. There's a topic when a resource is added, and the event contains the path of this resource and maybe different other meta type information. And then if you want to publish such an event, you need to get hold of the event admin service and then just send the events through this service. So in some Java code using the DS annotations from the Apache Felix project, it would look like this. So we have a simple component which has a reference to the event admin service, and this component simply sends out an event every 2 seconds and spams the whole system with very nice events, like I'm still alive with a timestamp when this event was created. So basically you just create first this event object and then call the event admin with send event, and the event is delivered to the interested handlers. Depending on whether you call send event or post event, it's either synchronously delivered or asynchronously to the handlers. On the receiving side, you can subscribe to the OSGi events by implementing the event handler service. This is using the whiteboard pattern. So you just register your handler with some registration properties, like in which in which topics you are interested. You can use additional filters, and then the event admin calls you whenever such an event occurs, and you get notified of the event. And again, just a simple example for doing this is here. So you implement the event handler interface, a single method named handle event. You get the event object, and then you can get the properties. So for my I'm still alive event, you register this event handler with the topic I'm still alive. So you're interested in these topics or in this topic, and then you can get the timestamp from the event object. So it's pretty straightforward, publish subscribe model. This is very good and works pretty well within the OSGi framework. So we are using it a lot. But it has some, I would not say problems, but it's maybe missing some things that you sometimes really need. One of it is the events you're sending are delivered immediately. If there is no handler listening, then the event simply gets lost. So usually this is fine for the use cases of the event admin, but there are situations where it would be nice to have some more guarantee. And there is no distributed eventing. So if you have a distributed system like a cloud installation, event admin only distributes the events locally within your single instance. And this led to different things. I'm just listing or explaining in this session here two of them. One is that we did some additions in the Apache Sling project to handle those cases and to implement the use cases we had. And then in the beginning of this year, we started finally this RFP, which handles distributed eventing. And I will start with the RFP. So this RFP right now, it's available on our Git location. You can download the RFP and then look into it. It basically describes an asynchronous remote eventing model with different kind of flavors. Because a lot of different use cases went into this RFP, and we tried to cover all of them. So it mostly will cover the usual broadcasting use case, where you simply send an event to all instances within your cloud installation or whatever it is. But you can also send a message directly from one instance to the other, have a reply mechanism, and then such nice things. And it also describes a quality of service model. So you may be interested in whether this, if there's a guarantee of delivery and how high this guarantee is, or how fast these events maybe are sent across your installation and such things. And the provider can advertise this quality of service, and you can select, depending on your use case, which one you want to use. You will also have a sender identification, so you know from which instance or from which service maybe the event was delivered and such things. And all of this should be language agnostic, so it should be possible to communicate with non-Java systems and send messages to other systems and receive it from other systems, maybe implemented in C or whatever. So this is the current state of this RFP. And into this RFP went different use cases, as I said, and I will start with two of them, which we provided, and they are all done in the Sling project. First of all, as I said, the event admin by itself is distributing events locally within the VM, within the framework, And when we started using the event admin, we had the use case to distribute these events across several instances. And we made a simple extension to the OSGi event admin, which is just an additional bundle you can deploy, and then it distributes events within your installation. And there's always a problem to distinguish between events you want to distribute locally and events you want to distribute across all the instances. There are different solutions to that. Some people have these use cases, some the others. And we just decided that the sender is the one who decides. It was our use case. So by just setting an additional property, event distribute equals true, the event will be distributed across the instances. And on the receiving side, you can query the event application property and then know that this is a distant event, distributed event. So if you want to use this and have the bundle installed, you simply, it's basically the same code as I was showing previously using the event admin. You just set this additional property, event distribute, to true, use the event admin, and the event gets distributed. So this is pretty simple, at least on the sending side. The implementation is a little bit more complicated. And on the receiving side, you can query this event application property and see it's coming from this or that instance. So this is straightforward, and it's just an addition to the event admin. Yeah, this is, as I said, one bundle we have in Sling. The sender controls the distribution, and on the implementation side, we are using a JCR content repository, which is an implementation from the Apache Jackrabbit project, which handles the distribution across the instances. But the API, of course, is independent from the implementation. This could be implemented with any other solution like Zookeeper or whatever you want to distribute messages. So this is first thing, so a simple extension to the event admin for distributing. And then we did one other very interesting thing, which we call discovery, and this is about topologies. Because usually, if you have a distributed system, you want to find out how your system looks like. So what instances are there, and how can you communicate between those instances? In the simplest case, you just have a single instance. It's pretty simple. But of course, you can have some distributed system with replicas. So in my example, you have three different instances. And in Sling, we have another nice bundle, which simply gives each instance a unique ID you can use. And this unique is persisted across restarts, so it's different to the framework ID. And then we have the notion of clusters. The simplest case, again, is a cluster of a single instance. And if you have more instances, they can form a cluster as well. And usually what we mean by cluster is it groups instances which are really in the same way provisioned. So these are really replicas of each other. They all have this nice ID, each instance. And the Sling discovery also does a leader selection. So you have a stable leader within your cluster. For a single instance, this is easy. If you have more than one instance, you have to do some clever computing to find out which one should be marked as a leader. And on top of this cluster notion, we define the topology. Again, topology can be a cluster with a single instance, a cluster with 3 instances, or to make it more complicated, as we have topologies which span different clusters. So in fact, what we define as a topology is a set of clusters. So just to have this notion. And this helps you to describe your cloud installation, by forming these cluster groups. And the instances in each cluster group are usually the same. They have the same running services, they behave the same, and so on. So just to explain the terminology we are using here. And this comes with some additional things. So we have this unique ID for each instance. You can have some optional description and so on for an instance, so we can find out the potential intent for the instance. And you can have additional metadata, like where this instance is deployed, in what data region, data center, and so on. And you can add your own properties by implementing so-called property provider services, which just add additional properties. And these properties of each instance are visible across a cluster. So you can see how the topology looks like and what instances you have running, and get these meta information. It's pretty nice. And as I said, we have this leader election as a stable ordering of the instances you can use to maybe do some clever distribution tricks here. And on the implementation side, if you're interested in the topology, you can use a whiteboard pattern, implement a listener service we have defined. And you get events whenever something changes in your topology. If a new instance is coming up, if it's going down, if the properties are changing somewhere, if the leader election changes because the leader went down or something like that. So you can use that to do some interesting stuff. And for those of you who attended David's and my talk about what's cool and new in R6, you probably heard of the RFC 183, which David presented about cloud ecosystems. And this is pretty similar to what the Sling topology does. In cloud ecosystems, there's a framework node status service defined, which is a remote service. And this describes an instance with all these different properties, like how to access the instance, in which data center it's deployed, and so on. So this is similar to the properties we have in the Sling topology. And then you can, as these are remote services, you have access on each instance to this set of services, and you can inspect which instances are available as well. So that's very, very similar. And in fact, you could implement one on top of each other if you want to. So it's nearly the same. And unfortunately, it came out, or putting it the other way, we implemented this in Sling before the RFC was created. That's why it's a different concept. Otherwise, I guess it would have been the same. And why do I present this? Because this topology stuff, or the cloud ecosystems specification, allows you to describe your topology, the instance you have. And on the other hand, you can use this information for distributing the events. So you know which instances are available. If you want to, for example, broadcast an event to all instances, by using this mechanism, you know which instances are there, right? And maybe you can do some filtering on the properties and just send the event to specific instances. So this is more or less the foundation for distributed eventing. And then the other use case we had is something we called job handling. This is a term we more or less came up with, and what we mean by this is that a job is an event where we guarantee that it's processed exactly once across the whole cloud installation. And starting such a job is done in the same way as you, or more or less the same way as you send events with the event admin. You have a job topic describing this job, and you have a payload of a key value map. And then you just create this job, and someone, hopefully, some service hopefully is there in your installation, which then processes the job. For the sender, it's or the sender doesn't care about who's processing it, but he knows if he sends such an event, someone will process it, and it's exactly one consumer who does this. So we have a very simple service interface, which is a job manager, which you can use to start such a job, and you can just specify the topic and the properties. So it's more or less the same way as we've seen with the event admin. And then for consuming, of course, someone needs to consume this event and does whatever it has to do. We define this job consumer interface with a single method. It gets the job and returns the result, whether the processing of the job was successful, it failed, it can be retried, and so on. So we have different ways of giving back the result. And then the central component here is this job manager, which handles the jobs and distributes them according to different rules and how the topology looks like. And of course, once a job is started by the job manager and distributed to some instance where it's executed, the job manager keeps track of this. For example, if the instance goes down while the job is processed, it notices that and then distributes the event to someone else, and it gets processed there and so on. So retry, failover, and all these things are handled. You can add notification listeners to find out what's going on, which jobs are processed, which were successful, and all these things. And just to show a different example, for example, if you have a backup job which you want to start periodically and then do some backup of your installation, you would define the topic, which is the backup topic in this case, implements this job consumer. The consumer does the backup when it's called, and then returns just, okay, everything went fine, backup is done. So implementing these jobs is pretty simple, as everything else, the retrying and then failover handling and so on is done by the job manager. You just have to do your task when you implement it. And then the very, very interesting part is the distributing of this job processing within a topology. Because, as I've shown earlier on, a topology can consist of clusters which have different, let's say, capabilities or different services running. So some instances might be able to process this backup job, others might be not because they don't have this service. And then the job manager knows through all this topology mechanism the capabilities, the processing capabilities of each instance. And once a job is started on any of the instances, then it can distribute the job to those instances who are capable of processing the job. And you can further configure this with queue configuration, so you can deal with how many jobs should be processed in parallel and how the failover handling is and all this stuff. So a lot of things to configure. And of course, as I said, if the topology changes and instances go down or new instances come up, all this is handled through this listener interface and so on. We also have progress tracking and then a history of jobs, so you can find out which jobs were successful in the last 10 days or whatever your query is. And all this is handled very nicely. And this brings me to the last slide, which is basically a roundup of the stuff I've presented here. So we started with the OSGi event admin, which is a non-distributed way of sending events within a VM, within a framework. And the other things I've briefly shown, like the addition to this event admin and this job handling we have in Sling, and several other use cases, as distributed eventing is really a huge topic, and there are so many different use cases, and everyone has different opinions on how it should work. And all these went into this RFP 158, which is, I think, currently voted on. And then will become an RFC, and then we'll come to solutions and so on, and just describe how things really should look like and how the interfaces are and how they will work. And all of this will most probably be based on the RFC 183, which is the cloud ecosystem stuff, which allows you to find out how your instances look like and what your installation can do and so on. And with that, I'm done with the stuff I've presented for you, but I'm pretty sure there are questions about this topic. Yeah, we can start at the back.
So did I get this right, that for the drop API, distributed drop execution, the drop description, the task itself, has to be deployed manually on the node that executes it, or how do you get the task information executed?
So for the execution, you have a service which processes this job, and you have to deploy this service to the instance. Yeah.
So it's not like a Lambda function that you just send off
No.
as a payload of the event.
Yeah. It's all done by services. Yes.
A little bit confused between the event and the job. Event can be consumed by any handler, could be any number of them, but jobs on one.
Yes.
And the job consumer being in a different instance, the same way an event handler could be. Like you could distribute an event outside the instance, and you do the same with the job.
Yes. Yeah. Oh, yeah. Yeah. Right. Yeah. There are different ways of how to process the job. I mean, first of all, you start a job on any instance with your installation, and it will be distributed to any other instance which is able to process this job. So it's transferred to or distributed to any other instance doing that. And you can also do something like setting up a separate instance for, let's say, some heavy jobs. Like, for example, what we are doing video encoding, which is very time and CPU consuming. We have separate instances just for that stuff, and those jobs are distributed to those separate instances. And all the other normal jobs, which are simple, fast ones, are done by any instance in the installation.
Can the job manager handle dependencies between jobs, or run jobs, several jobs on the same machine, for example, if they need to share data?
No, right now there's no dependency between jobs, or no, let's say, ordering or shared data model or something like that. It's just single.
Really dependent on each other.
Yeah. But of course, they can write into the same, let's say, data store, and then share data using that. But it's also no workflow engine where you can say, once this job is finished, do that job or something like that.
Any more questions? If not, I got it. You talked, when you talked about jobs, you talked about the system dealing with failures of event consumers. Does it also tolerate failures of job manager?
There are no failures in the job manager. It's implemented perfectly. That's no problem. But what kind of failures do you mean in the job manager?
So you said that the semantics are that it's exactly once.
Right. Yeah.
And so what happens if the process the job manager is running and just fails?
Okay, I see. Right. This job manager is also a distributed service, so it's running on all the instances. And if one of them goes down, but was processing or has had some jobs in its queue, then the other job managers take over and handle that case.
And they know the status of
Yeah.
each job.
Yeah. So all the status of all the queues we have and all the jobs are distributed across the instances as well. So each instance knows what to do. And because we have this leader election, we can always dedicate one instance doing the failover.
Do you run like a consensus algorithm
Yeah.
to elect a leader?
Yeah.
Is it also persistent? Or
Yes, it's all persisted, yeah. Including a history, so we can find out later on which jobs were successful or failed and so on.
Is it possible to sum events and send it as one compound event? For example, I'm interested in a timestamp every second, and every 2 seconds I like to have the information how many bytes I have in my store. So this would be increase the amount of events by 50%. And if I know I send every second event over the network, I could sum this information into some kind of compound event.
Right. No, there's no notion of that. So you would have to take care of that by your implementation. Just sending one event and then the other one. Yeah. And alternating between them.
I got one more question. On RFP 158, you mentioned that it talks about quality of services.
Mm-hmm.
Are there any specific ones that the RFP asks for, like exactly once, or at least once, or
Not yet,
cost
no.
of delivery, or
No.
whatever?
No. The RFP is not talking about it yet. I mean, yeah, the RFP is not talking about it. We will define some of them in the RFC, whatever these are. Yeah.
So it will be defined in the RFC. It's not going to be
Yeah.
left as an extension.
I mean, the providers or the implementers of the specification can add own characteristics, but we will define a meaningful base set for that.
Okay, good.
Yes.
And the also says that the provider of the event has to undertake the event to be distributed, right? It's not a property eventing. So
This is if you're using the distributed eventing. Yeah.
yeah,
Mhm.
this will be in the spec, right? Or at least it's
Yeah, the extension of the spec. Yeah. Mhm. Yeah. But this is always a hot topic of how to do that. Other people think it should be done differently by defining, for example, which topics should be sent over. Yeah, we took the simplest way and just let the sender define it.
Any more questions? Thank you. That was very good.